and indicate with a graph how this quantity can be interpreted as an area. So the general idea here is that if you have a graph of velocity and time, if you find the area, that's the distance.
Okay.
So we're going to do that for this problem, but we're going to do it with rectangles. Okay, so velocity and time here, 20 kilometers per hour. So that we'll call this 20 for 2 minutes. This is 2 minutes here, and that's 20 kilometers per hour. Then for 3 minutes, it goes 12 kilometers per hour. So that's here. So that's 5. And then for the next minute, it goes 40 kilometers per hour. This looks something like this.
Okay.
So there's 3 rectangles here. So we've got to find the area of each rectangle. The area of the first rectangle would appear to be 20 times 2, but this 2 is in minutes, and the kilometers are in kilometers per hour. So it's 2 minutes times 60 minutes and 1 hour.
Okay.
So in short, it's 20 times 2 over 60. Plus the second one here, the second rectangle here, it's going 12 miles per hour. It's set for 3 minutes. That's 5 minus 2. So it's 3 minutes, or 3 over 60. Plus the third rectangle.
Well, isn't it 3 minutes times 1 hour over 60 minutes? Isn't it?
Yes. I'm just shortcutting that
okay.
part, that conversion. And then for the third one here, it's 40 kilometers per hour times 1 minute, 1 out of 60.
Okay.
And then from here, it's just simplifying this answer.
I know this doesn't have anything to do with this, but you know, like the box method for integrals?
Yes, it's very similar. So these are Riemann sums. Riemann sums use the same width every time. These are different widths, which you'll see on the AP. Go ahead.
These are Riemann sums?
The Riemann was a guy who came up with this idea. Riemann sums use the same width of rectangle each time, whereas
Okay.
these are not the same width. They're different widths.
Okay.
So this is 1 over 30. So this ends up being 2/3 plus this is 1 over 20. So this is 12 over 20. And this is 40 over 30. This is 2/3. So this becomes 4/3 combining these two. And this is looks like 3/5. And then you can combine these together. So that's 20 plus 9. So this is like 29 over 15 kilometers is the distance traveled.
Okay.
All right, so let's look at number 3. Number 3 is sort of a word problem. It's got a lot of extra words that really just tell you to calculate a Riemann sum. So the time here is from 0 to 2 hours. So if you were to make a graph of this information from 0 to 2, it's 0.5 is the height. So I'll call this 0.5 right there. So that's 2. And then from 2 to 4, it's 0.3. So that's there. So what ends up happening when you start doing these, and you may just want to put the height above it.
Okay.
Since it's not really always going to be possible. 4 to 9. So that's 5, 6, 7, 8, 9. That's 1. So height of 1. Then 9 to 12, 10, 11, 12. So you start drawing the picture and you realize, oh, maybe I can just like do something different. Meaning, can you just calculate this by multiplying? And the answer is yes. Like you can take 2 times 0.5, because that's this first rectangle. First, the area, which is the total rainfall, it's 2 times 0.5 for this first rectangle, plus
4 times 0.3.
You would think 4, but it's 4 minus 2, so it's 2. Yeah, so it's 2 times 0.3.
So that's 5 times 1.
5 times 1 plus
3 times 2.5.
Yes, 3 times 2.5 is 8 times 1.5 plus 4 times 0.6.
Okay. And then that's the total rainfall? Yes.
Yes, yes, when you get all whatever that is.
Okay, cool.
What we have not done is used an equation area. We've had a table.
Uh-huh.
Like 4 is gives you an equation. 13 through 18 give you equations. 7 gives you an equation. Like those might be good to do if you thought those would be on there or you wanted us to cover that.
Which one's 7, 13?
13 through 18, they're
Yeah,
equations.
let's do one of those. Like the 13 through 18 group, maybe.
Okay. Do you have a preference?
Oh wait, are these um are any of these like integrals?
They are like 13 through 18 are the
Yeah,
Riemann sums.
let's do one of those. I don't care.
Okay. So
Can you can you over like both the box method and then also like the I don't know what it's called, but like the one that looks like an S?
uh,
Like it's
okay. Like the box method is that, I mean, that's what we're doing. We're making rectangles. I guess I don't know what the S method is
like
referring to.
the one I don't know what it's called. Hold on, let me pull up my notes. Um, like do 10.3. I'll find it. We can just do
Okay.
this one.
Okay. So I'm gonna actually do a left 6 on this because you're not doing M's as far as I know. So
Yeah.
left sum on this, you have to first compute delta x. Delta x is b minus a over n. This is a, this is b, 5 is a, 8 is b, so it's 8 minus 5 over n. N is this number here over 6. So this gives you 3 over 6, which is 1/2 or 0.5. And then what I like to do is I like to write, I write all the x values out, kind of like making a table. So there's 5, because that's where you start. You always start at A. And then you add. So it's 5.5, 6, 6.5, 7, 7.5, 8. Okay. And then there are f of x values at each of these positions.
Okay.
So for a left sum, you're using like these 6 over here for a left sum. And for a right sum, you use the 6 over here on the right that I boxed in. It's like a left and then a right sum. So the left sum here is delta x times, and then you have to multiply by, you start out at f of a plus f of a plus delta x plus f of a plus 2 times delta x, and then so on. It's a little bit confusing. For this problem here, your delta x is 0.5, and then you do f of 5 plus f of 5.5 plus f of 6 plus f of 6.5 plus f of 7 plus f of 7.5. And those are all numbers we're going to get. We're going to get by putting them into the original equation. So your f of x here is you're putting 5 into this thing here. So that's 4 times 5, 20, 20 plus 3. Okay. So then the next one here, 4 times 5.5 is 22, plus 3 is 25, 27. And this one has a nice pattern. It actually goes up by 2 each time. Okay, so now that we have those numbers, it's basically like a table problem. So the ones when you're given an equation, you essentially want to make a table and then use that table in the formula.
Are these this Are these like partial sums?
No, partial sums are for a geometric series or for series.
Oh, okay.
Yeah, this is totally different. So f of 5 is 23 plus f of 5.5 is 25 plus 27 plus 29 plus 31 plus 33. And then you multiply by 0.5 for your left sum.
Okay.
Your right sum is really similar. I know it doesn't ask for that, but your right sum is really similar. It just uses the 6 on the right. So it's 25 plus 27 plus 29 plus 31 plus 33 plus 35. So notice like the one on the left doesn't include the 35. The one on the right does include it, but doesn't include the 23. And that's the difference between them.
Okay. What I was talking about was like in my book it says like find the definite integral by computing an area, and then it says
Yes.
it helps to look at a graph of the
Yeah.
function.
So like what they're saying is if the function here f of x equals 4x plus 3, if you were to graph this, it looks something like well, this isn't drawn to scale, but it looks something like this. Oops. And from 5 to 8, you're trying to find this area. You're supposed to know what shape this is. This is a trapezoid.
Oh,
So you go back to your geometry book if you need to, and you say, oh, area of a trapezoid is 1/2 b1 plus b2 times the height. The height though is here, and then this is b1 and this is b2. These points up here.
okay.
So you're in this case, b1 is what's going on at 5, and we just said that was 23.
Well, they
And
give you
what's
like that. I say S, but it looks like an S, and then there's like a number on the top and then a number on the side.
this?
No,
This?
yeah, and then there's like a number, like it's like 7 and 3, and then like to the right it says like 5 dx or
Oh, this symbol, like this.
yes. I
Yeah,
don't know what it's called.
yeah, this is called an integral. This is way beyond where you're supposed to be in this class. Um,
Oh,
so I mean, is your instructor expecting this? I mean, this is the second part of calculus.
I don't know. It just says find the definite integral. So, but
Yes, and that's what we're doing. So
okay.
what this is the area.
Well, yeah, they just like give you that symbol, and then I think you're like supposed to apply it to the graph, right?
Yeah.
Okay.
So the graph here, just finish this off, this calculation. The value at 8 is 35, and then the height is the 8 minus 5, and that's whatever that is. That's your definite integral.
Okay.
Sometimes they give it to you. They ask for like they say it's a circle, and you're supposed to remember how to find the area of a circle, pi r squared. But sometimes it's only like a quarter circle, so you have to take a quarter of it or half.
Okay. Okay. So then. um, Oh, can we do 298 on the last page, like 53 to 60 to compute the area under the graph?
Yeah. Okay. So I think we should do. I guess we'll start with 53. The find a formula for Rn and compute the area in the graph as a limit. So you're supposed to eventually come up with the limit as n goes to infinity, sigma I equals 1 to n, and then you put something in here. Does that seem familiar from class?
Yeah, I think
Okay.
so.
All right. I need to go look up some notation on this because I haven't had to do any of these in a while. So area under the graph, under the curve as a limit. You have that formula because there's like a few as a Riemann sum, limit. You have to do a few things like x becomes a plus delta x or something like that.
Yeah.
Let me see if I can find something really quick. Um, so it's like f of xi times delta x. So f of xi delta x. Delta x is still b minus a over n, but I think so xi starts at a. So your b minus a over n here is 1 minus 0 over n. So delta 1 over n. So this is the limit as n goes to infinity sigma. Just not finding the right. Yeah, it's okay. So it's a. This is really correct. It's a plus I delta x. Because sometimes, and I bet your instructor this, it's a plus I delta x. Because your instructor will definitely not give you the won't have you start at 0 always.
Yeah.
And that's a right there. Um, let me see if I can find one more example here. Sorry, I'm really struggling to find the right notation. This is not what I wanted. So you're
Well, she had it as areas under the curve. She's at like what's it called a summation symbol, n, and then on the bottom c equals n f of xi delta x. That's how she wrote it.
yeah. So that's what's going on. So you have this. So this f of a plus I delta x. You have to take this and put it into that equation there.
But is that the same thing as xi?
Yeah, yeah.
Okay.
So yeah, because well, I guess I don't know where you're going with this. Do you actually have to use the area formulas, like the fact that sigma I?
Well, she just says like know how to compute area under a curve and what that means.
Okay, I mean we're very far away from that, I guess. Um, yeah, I mean this becomes I squared over n squared times 1 over n. This becomes uh, uh, sigma. So this reduces to limit n goes to infinity I squared over n cubed, because there's two n's there, and then the n comes out. So this becomes the limit as n goes to infinity 1 over n cubed I squared. And then there's a formula for this. This part, like this is one of those known formulas, but this seems very far away from what we're supposed to be doing.
Yeah. Okay.
Uh, like this, like what we wrote up here. Sorry, goose. What I was trying to write up here, this produces this notation, this integral x squared from 0 to 1 dx.
Yes, that's what. Okay, that's kind of like what she has us do because.
But there's all these steps in between where you can see how the I squared is really the x squared.
Okay, like here's an example that she gave us. Like.
Okay, so maybe you could send. I don't know if it's possible to send it over to me.
Yeah. You can do that. I'll just email it. These are just my notes, but like in the middle of the page, like below is a plot of blah blah blah.
Let me know when you sent that over. There it is. Okay, got it. Okay, I see a page here.
Yeah, so like the ones like below is a plot of f of x equals blah blah blah.
I only see a page that it's maybe you just, oh, there you did. You just sent something new. Okay, there it is. The one below the graph, or let me.
The one that says below is a plot of f of x equals 1 over x squared.
Yes.
And then like also my notes are kind of covering it, but sine x over x. That.
Yes. Okay. Yeah. So let me snip all that in, and then I think we can make some clarity. What I was trying to do is you should try to ignore everything I just did because it's not helpful. What your instructor is trying to get you to see is that the limit as n goes to infinity, sigma I equals 1 to n, 1 over x squared delta x goes to, this becomes the integral, okay, 1 over x squared dx. So basically, these are the same. Instead of delta x, you write dx. And then this is your a to b. So in your case, the a to b was given as, well, I don't know what it was given as, but
Or -1 to 2.
negative 1 to 2. Yeah, so -1, so this would be -1 to 2. So if you're doing sine x over x, which actually has an issue at one of the places, but if you're trying to find the limit as n goes to infinity, sigma I equals 1 to n, sine x over x, delta x, this goes to, again, you write this symbol instead of the sigma. You write sine x over x and dx instead of delta x, and then you just write -1 to 2.
So how do you write that as like a limit?
The limit's over here.
Oh, but isn't that the sum?
It's from like the sum, when you take the limit of a sum becomes an integral.
Oh, okay.
Limit of sum becomes an integral.
Okay.
Now, your instructor is making some point on the right here about sine to area, which is totally correct and everything. but the integral takes that into account.
Okay.
If unless a different question would have to be asked for it.
Okay. So you don't really have to do like any like calculations for those.
No.
Well, the one on the top, it says the f of x equals 1 over x squared, the one we did.
Mhm.
Why does she, it says D and E. What is it?
Well, this is way beyond your class, but it's because it's undefined at 0, and you can't integrate something that's undefined at 0. So like what I wrote up here really isn't correct, but notationally it's correct because it's what she was asking. But at 0, the function is undefined, so you can't find the area under it.
Okay. So most times they would just, like for pre-calc, it would just like give you a shape and you would just have to use like the area of a triangle.
Triangle, trapezoid, maybe a circle. Those are the ones worth knowing or remembering.
Okay, so I think we're good on the packet. And then the other thing I sent you, the earlier attachment, was a function analysis one.
Okay.
And she said that for the function analysis, it's not going to be any no trig functions. Yeah.
Okay. I'll snip it in. We'll look at it.
That one was one from our first midterm. But...
Okay. All right. So domain of this thing, we'll start with that. You can see can't divide by 0. So it's everything but 0. 0 is where you're problematic. So it'd be minus infinity to 0, union 0 to infinity. Range is a little bit harder. I guess you can we could do that now, but you would have to know something about this graph to be able to do that. So I'm not sure if we can do that or not. And you're not supposed to use a.
Well, this test, she had us. She let us use a calculator for everything but the function analysis.
Okay. Well, here's what we know. We know the function is defined everywhere but 0. Okay. So what we can do is we can test a point smaller than 0 and bigger than 0 to know whether it's positive or negative. So it's usually the positive numbers either. So this is positive, but you'll find that this one's negative. So the graph switches signs there in terms of like above or below the x-axis. Since it's growing, and or not, I shouldn't say it's above the x-axis, and here it's below the x-axis.
Okay.
The local extrema. This is really weird. I don't. Well, okay. So let's go to other. So what's that?
Can you graph it first and then do all this stuff?
Well, if you could graph it, you can get all this information. I'm trying to do without assuming that. Did you say you could graph this or not?
Well, on the bottom of this page, it says provide a possible sketch.
Well, yeah. I mean, that's not super helpful. I mean, this is actually a question you would get in calculus because you can actually do all these things by hand, but I have to sort of do them without that. So horizontal asymptote, let's look at that, or vertical asymptote. There's one at x equals 0 because that's where the bottom is equal to 0. The horizontal asymptote, so it's what happens as x gets large, and we don't know. You have to decide, well, which grows faster, 2 to the x or x?
2 to the x.
2 to the x. So when you go to the right, this thing grows because 2 to the x is going to grow faster than that, even though you're dividing. But the other way, this is what's interesting. The other way, it's 2 to the like negative whatever, negative 500. That 2 to the negative 500 is like 1 over 2 to the 500, which is really small, and you're dividing that by 500. So you basically have 0 divided by a number. So there is one at y equals 0. Because this 1 over some gigantic number
that
over
would approximate like 0, or
yeah, approximately 0. All right, so that's so then okay. So we've got a few things we could say. The limit.
Well, those are always No, those are only first sign.
So as x goes, we kind of already did this, as x goes to positive infinity, f of x also goes to positive infinity. As x goes to minus infinity, f of x goes to 0. And that's what we just said by sort of trying to figure out these asymptotes.
Yeah, okay.
Okay, y-intercept we can do. We will get to these other ones, but I'm kind of avoiding them. The y-intercept is when x equals 0, but x cannot equal 0, so this does not exist.
No way. Okay, no way.
Yep. Y-intercept is when y equals 0, so the only time this can equal 0 is if 2 to the x equals 0, which is also not possible.
Okay.
So this, I mean, this is hard to imagine without seeing this. What does the instructor mean by bounds?
I think just like upper and I don't know, like upper and lower bounds, or wait, let me see.
Yeah, I don't know what this meant by that, but we can get back to that. So, so here, I mean, if we kind of are drawing a sketch, we now have this local extrema, 1 point at 1.443, comma 1.884. So here's what I take that to mean. 1 point. So there's something going on kind of here. We know there's a vertical asymptote there, and we know that the other way it approaches 0. But this other thing seems to grow, and there's a vertical asymptote. So this is kind of the sketch that I'm seeing for the right side, because it has to go to positive infinity for the vertical asymptote, and then there's that there.
Mm-hmm.
But then what happens on the other side here? Okay, so it's so we almost have to pick a number really close to 0, like 0.00001, and see what happens. And or negative 0.001.
Can you like plug in points to make? I mean, like plug in numbers for the x's to like make the graph.
Yeah, but but you'll get these points that don't really, like if you put -1 in, you'll get -1/2 over -1, which is -1/2.
Okay.
And then if you put in like -2, you'll get -1/4. I'm sorry, 1/4 over -2, so you get -1/8. And you'll see this thing kind of doing something like this, but you won't know what's happening here until you pick a number really, really close to that.
Really, really close to 2.
Really, really close to 0, like minus 0.00001.
Okay.
So 2 to minus 0.00001 is 1 over something, 1 over, and then this is and then it's over that, so it's like multiplying by that. So it's like which grows which takes over sooner. Yeah, this is really I wish we could use some calculus here, but we can't. It does this, and that's what's really hard for me to convince you of, is that it goes this. But if you try a number like that, you'll see it gets there.
Well, okay, I think what should isn't this one like unbounded? Like there's nowhere, or I don't know what you mean.
So the unbounded could mean like is there an absolute max? And the answer is no. Is there an absolute min? And the answer is no, because it just goes down forever, it goes up forever.
So I think it's just unbounded then.
Yeah.
Okay.
So this is just information. Okay, not particularly useful. So now we can do this range. The range is the y values.
Right.
All right. So there you can see that it goes from -infinity to 0. That's this part here.
Yep.
And then this is the min. This is the 1.884. And then it grows to infinity from there.
Okay. Then it's increasing from the 1.884 to infinity, right?
It's the x value now though, 1.443. But yes, it does go to infinity, and then it decreases in 2 regions. It decreases here, so minus infinity to 0, comma, 0, 0 to this 1.443. It's going down there.
Okay, that makes sense.
This is really tough, by the way. I mean, without a calculator, without calculus, it's really, really challenging.
Yeah. Okay, cool. I don't know. I don't like have another one on here.
Okay. There are some other things in the review packet to look at, or
Not really sure. What
oh yeah, I don't know.
I
Uh,
just like went blank. I swear.
yeah.
I was. Oh, I said I didn't have another one of these like on hand because the other one was a signed one that she gave us, but I don't know if you can come up with another one.
I can come up with parts of it, I guess. Um, you said no to.
She just says, read it. She said, no vectors, no trig function analysis or function transformations.
All right. Well, I'll give you kind of. I guess I'll give like an easier version of this question, but it's still really, really horrible. So this time we'll do it for natural log of x over x squared.
Okay.
Okay. So we said before, and this point is 1.649 comma 0.184. So this time the domain, you can't divide by 0, but what about natural log? What's the restriction on what can go inside the log?
Uh, right.
Only positives.
Oh, okay.
Okay.
Set down my sheet.
All right. Now,
Do you have to use like E here?
no E stuff. We'll start with vertical asymptotes.
Okay.
So it's where the bottom equals 0, so x equals 0 in this case. Horizontal asymptote. So what you're trying to decide is which grows bigger, and you actually need calculus to do this. So that's where I don't know how to tell you what to do other than you have to realize, okay, that's what natural log looks like. That's what x squared looks like. Which grows faster?
X squared.
X squared. Yeah. So that means you can kind of ignore that top one and say it's kind of 1 over x squared. Well, that has a horizontal asymptote at y equals 0.
Because because the bottom one grows faster.
Yeah, it's like
So what if
1 over. Go ahead.
the top one grew faster? What would it be?
Sorry, I have no idea what this is. Let me see if I can.
Both having some technical difficulties today.
Okay, there we are. We're good. We're good on this. So if the top grew faster, and that's what we actually had in the last problem, it goes to infinity.
Oh, okay.
So
Wait,
in the bottom,
but why did we put horizontal asymptote equals 0 on the last one?
because you had to go both ways. You had to go positive infinity and then negative infinity.
Oh,
So
okay.
negative infinity, it's over here. positive infinity. So this one only you only have to look at positive infinity because that's where it goes to. So the limit, I'm sorry, that's not what we're doing here. We're doing as x goes to positive infinity, which grows faster, and we said, well, the bottom one does, so y goes to 0, or f of x, I guess. That's how you're doing it.
Uh-huh.
Now it's not as x goes to negative infinity, now it's as x goes to 0.
But it goes to infinity.
It actually goes to negative infinity. Because even though you're squaring that number, like we're looking at numbers like 0.0001.
But isn't the graph of x, the one we're doing is x squared, right?
Well, no, when you go to 0, you have to look at them both again.
Oh, okay.
Okay, so then the natural log of 0.00001 is a negative number, some sort of negative number over something squared. When you square it, it gets smaller, but then when you have a 1 over a really small number, it becomes bigger, and that's why it goes to negative infinity.
Okay.
There's a lot there.
So then it's like increasing from 0 to infinity. Right?
Maybe we have this going on here. And that's why you got to be careful here. So the x-intercept, we can there is no y-intercept because that's when x equals 0, and that does not exist. The x-intercept though does exist this time. It's where does the natural log of x equal 0? And you said, hey, do I use e? Well, yeah, you kind of use e here. So x equals 1 for that.
Oh, e to the 0 equals 1. Okay.
Yeah. So here's what we have so far. We have this 1, 0, and we have a vertical asymptote, and we know that it does this. And then I give you this point 1.6493.184. So that's like right there.
Okay.
And we know that it goes. Sorry, that's not what I want. So we know that it goes to there. It goes along here. So the graph, you kind of have again kind of some information to do this, but it looks like that, where it
Okay.
comes up, hits it, and comes back down.
Oh, it
So
goes
that,
back down a little. Okay.
yeah, because it has to approach the y equals 0.
Okay.
Okay, range. Now we can do range. Range is minus infinity, and then there's the maximum value at 0.184.
Oh, okay. Yes.
Increasing behavior. So it increases from 0, looking at x values. These are x values, and same with decreasing behavior, looking at x values. It increases all the way up to 1.649, but then it decreases the rest of the way here. So 1.649 to
Negative
infinity,
infinity.
positive infinity, because you get to the right. You're going to the right.
Oh,
You're looking at
right.
the x
Okay.
values.
Right. Okay.
Now bounds, this one actually has an upper bound, upper at 0.184.
Oh, okay.
See, that kind of bounds it
Yes.
there.
But is there such thing as like a left bound because of the vertical note?
I guess, yeah. I don't really know what your instructor means here, but you can say left bound at at x equals 0. It's negative infinity. I don't really know what they want, but it's
I mean,
more
I think she
like,
just wanted like upper lower.
okay. So there's graphs though. There's graphs that do this where they go. And they're kind of bounded like this. I think that's what she's referring to.
Yeah.
This
Okay.
one does not have that, so it's only got an upper bound.
Okay. Cool. Do. Yeah, I wish she gave us a calculator for that, but
Yeah.
no. Okay. The only other thing I wanted to do was back on the packet
Yes.
on page. Oh, what page is this? 546.
Okay.
any of them, or maybe like 47, or like
47 is good to start with.
46 or 47.
Let's start at 46 because it's an even. You may not have the answer to this. So it's very much kind of looking at like what we just talked about, and we're looking at what happens as we're trying to find the limit as n goes to infinity. So if you were to just graph this top one, you would get -1, +1, -1, +1. This one is bounded. This one goes from -1 to 1. You follow that? This top part?
How do you know that if you don't graph it?
It's an alternating. This one's always what you use for alternating. It's just -1 to the power of n, or n plus 1, or.
Okay. Yes, that makes sense.
The bottom one here, if we were to graph that, square root of n, it looks like that. So it goes from 0 to infinity in terms of its range.
Right. Okay.
So out at infinity, when we go really far out on this thing, it's either 1 or -1 on the top over infinity, or it's -1 over infinity. Those are both 0. So the limit as n goes to infinity, c sub n is 0 because of that.
Okay, because you're dividing a small number by a really big number.
Yes.
So that converges.
Yeah, I know you didn't ask for this one, but I just want to comment on 45. We can do another one as well. Cosine n. If you look at cosine, it's bounded between -1 and 1. N grows forever. It's kind of the same problem. It's like -1 to 1 over.
Because that's just like linear.
Yeah, 0 to infinity. So it's the same deal. It becomes 0. Yeah.
Okay.
Now you said maybe 47.
Yeah.
Okay.
So like the easiest way to do this is to just think about them in terms of their graph then?
Yeah. So this one, you got to use some properties. This is n natural log of 5. And then minus natural log n factorial is n times n minus 1 times n minus 2 times n minus 3, and so on. And we need that because we're going to have to break this apart a little bit.
Okay. So then.
So on the right here, this is natural log of n plus natural log n minus 1 plus natural log n minus 2, and so on.
Okay.
You're always subtracting that. And then this is n natural log of 5. So this one grows. This one grows really slowly because it's linear. It's n. N is like x. This is like x times a number.
Okay.
So how does that compare to the growth of all of these? Is the question.
Will that grow? Will the right side grow like really fast?
Well, I'm not sure because the natural log doesn't grow very quickly, but you have so many of them. You have like natural log of, it's like that one, and then you have another one you're adding to it, but you're going on forever.
But isn't like the factorial?
Yeah, I think the factorial grows, outpaces it. So whatever this is, the one on the right outpaces it.
Okay.
So you would say limit as n goes to infinity, d sub n goes to minus infinity because this is negative and these outpace it.
Because you're like subtracting a bigger number. Okay.
Yes. Like all these add up forever, so they eventually overtake whatever that is. You just keep adding. It's very awkward, but that is what is ahead of you. So. Okay, this is a place for us to stop. I will send you the notes out really quickly here. As soon as the Zoom recording finishes, I'll send this over to you. So you'll see it soon. Okay, thank you. See you next time. Bye.